Hi, my name is Cameron Ball, and this is JT Herboldsheimer, and today we'll be talking to you about lab report number 6, which really talks about flow loops through piping. And so on the left here is a configuration view of our pipe, and so this top pipe is our galvanized pipe where water will flow through. Below is a PVC pipe that's just a straight shot through, and then the third one is a PVC pipe with T's and elbows in it. So quick introduction. Basically in this lab, we're using a water flow loop to calculate major and minor losses. The major losses will be from friction factor and the minor losses will be from just the geometry of the pipe. As you can see over here in figure 2, there's a significant amount of geometry in this third one, some geometry here, but really we're taking a look at that third one for the minor losses, and the first two are our big friction factor ones. And so also in this slide, we're really talking about the orifice plate and its validity in measuring flow rate. And so at the end of the day, we're going to calculate these friction factors and loss coefficients, and then we're going to compare those with reference values from the Munson and Young textbook. And so 15-foot length of galvanized and PVC pipes was used, and then the series of T's and elbows is once again that third pipe. JT will talk about the methods briefly.
So for this lab, some data that was provided for us was various pressure drops across areas of interest. As you can see in figures 4 and 5, there's little nodules that we can attach the pressure difference meter to gauge the pressure difference across the elbows and T's. As well as pipe dimensions were also provided and flow rates via flow meter. And so figure 3 shows this flow meter that was used. And then again, figures 4 and 5 show the elbow series and the T series. So now Cameron will talk about some of the equations that he used for parts 1 and 2.
Yeah, so thanks, JT. The first equation was just a Q ideal, which was just finding that orifice plate ideal number for the flow rate. So that was used to calculate the orifice coefficient, which we took a digital value and divided that by the ideal. And so that gave us a overall coefficient that was then used to really calibrate the rest of the data, which is what you see with the Q actual is equal to C naught, I guess CO, so that's the orifice coefficient, Q ideal. And so that's how we got most of our actual values. It's a little bit of a funky process of calibrating it, but it's a model of what the real world situation looks like. So the equations 4 and 5 are our friction factor and our minor loss coefficient. So now for some uncertainty, the uncertainty of the digital flow meter is just a randomized student t-test. And so then we jump into the Q actual, which is a fairly complicated equation, which breaks down using the Q ideal and the orifice coefficient uncertainty equations as well. And so that's what those look like. And so now JT is going to talk to you about the friction factor and the KL uncertainties.
Yeah, so the uncertainty in both the friction factor and the loss coefficient are both dependent on the differential pressure as well as the velocity term, which is a function of Q over A. And so the only other variable was Q that was changing. And so as you can see in these uncertainty equations, that's what we used dependent on the delta P and the Q. And so now it'll be back to Cameron to start to talk about the discussion.
Thanks, JT. So part of this lab was taking a look at the pressure drops in the system. And so as table 1 illustrates, there's an expected pressure loss that comes from taking the inlet pressure to the pump minus the outlet pressure to the pump, and just finding the absolute value of that. And so as you can see, those are massive numbers, and then the measured pressure loss is a very small number. And so basically what happened to create this difference is we took measurements all around the geometries that we were interested in, like the 4 elbows, the 4 T's. We didn't take into account all of these other elbows, like this first one here coming out, or this one here in the back, or any of the valves or any of the screens throughout the system going to the pump or the valves, wherever they might be located in the system. So those play a significant role in increasing the pressure losses to the system, but we just did not take into account those. As JT was talking about earlier, the 4 L's and the 4 T's had those pressure differential meters on them so that we could tell those differences, but there's a lot of geometries and other things that are unaccounted for causing this significant difference. And so then moving on to part 2, the flow rates were calculated once again using equations 1, 2, and 3 with the normalization. And so overall, this table 2 just really goes to show that the orifice plate provides a very accurate measurement of the flow rate once it's been calibrated correctly. Like the largest difference we found was 1.77%, which is relatively minor. And so at the end of the day, the orifice plate does a great job of accurately calculating the flow rate. The only minor concern about it is the calibration factor. But once again, that can be mitigated easily. So now JT is going to bring us home talking about the friction factor and the loss coefficients.
Thanks, Cam. And so part 3 had us calculating the friction factors for the 15-foot section of galvanized pipe, as well as the PVC. So table 3 shows this data, the calculated friction factor with uncertainty, as well as the Moody chart values that we calculated in the pre-lab, and then the percent error in the last column. And so looking at the percent error, that's comparing the Moody chart values with the calculated. And so as you can see, the calculated values are very, very close to the Moody chart values. And so these calculated friction factors are valid. And so then for part 4, we were asked to calculate the loss coefficients through the T series and the elbow series. And so table 4 shows this data again with uncertainty and then the textbook loss coefficient and the error. One important assumption that we had to make for this part was that the T's and elbows were threaded. We made this assumption because when we looked at the flanged loss coefficient, it just didn't seem like it was a very good comparator for our data. So that is why we used the threaded. And so, yeah, as you can see, looking at our calculated minor losses, looking at the percent error, they are very, very similar in all cases. And then when you look at the overall section of all of them combined, the loss coefficient takes a big jump up. And so this tells us that delta P is affected by the number of components. And so that's a very important thing to take in consideration in any future projects. And so, yeah, in wrapping up, this is our sources page where we got those loss coefficients as well as some of the orifice plate dimensions and equations. So this is our Lab 6 report. Thank you for watching.
Thank you very much.